Dr. Stephen Ferguson. We have decided that one of us will introduce our plenary speaker, and the other one will chair the Q&A session. And I was the lucky one who was assigned to introduce our plenary speaker, Dr. Francesco Magliavacca. He's a full professor at Politecnico Milano, and he's previously worked in London and Minnesota, and in Michigan, sorry. And he's an expert in many different fields: pediatric, cardiovascular mechanics, fluid mechanics, materials and biomaterials for application in cardiovascular mechanics. I think it's a very good opportunity for the community of fluid mechanics in this ESB society, of having the opportunity of reviewing some of the important topics we have in this field in our society. So I'm sure it will be a very, very, very interesting session, and the topic of, or the title of the presentation will be combining in vitro and in silico approaches towards patient-specific cardiovascular study. Please, Professor Francesco Magliavacca, whenever you want.
Thank you, Mr. Chairman, for the nice introduction. Thank you, Xavier, for inviting me to this conference and having the opportunity to show the study that we are doing. I'm from Politecnico di Milano, which is one of the three technical schools in Italy, which is in the north part of Italy, and is a school of engineering, architecture, and industrial design. And I'm working in a laboratory, which is a laboratory of biological structure mechanics, which is a constellation of different laboratories. So we have a laboratory of prosthetics biomechanics, we have a laboratory for micromechanics, of tissue mechanics, we have also a part dedicated to medical micro devices, and we have also a laboratory of life support system. All these laboratories do experimental activity, which is linked also to computational part, which I will show you in a moment. How is our experimental equipment? So we work on a multi-scale level. We can go from nanoscale measurements. We have a non-indentar and microtensile experimental machine that can also work under scanning microscopy. We work at the microscale, and of course we have also a machine, testing machine that works on a micro scale. These experimental activities are linked to a computer center, and we try to use both with an approach that I will show you in a moment. So regarding structural simulation, that can be done in our center, we can do also fluid dynamic simulation and also mass transfer and thermal simulation. This multi-scale approach, of course, can be applied to the computational side of the research that we are doing. The approach, as I'm trying to tell you, is both experimental and computational. Why we like to do both these, to apply this approach? On a side, because the experimental one allows us to validate computational prediction, because with experimental activity we can have measurement of quantities that cannot be simulated or to be used in the simulation, and on the other side we can have a calculation with the computer simulation, with in silico simulation, calculation of quantities that are not measurable during in vitro experiment. We can have design of experimental activities. We can use the in silico results to make an interpretation of the results that we obtain from experimental activity, and this is also a part that I will show you in the topic that I will show in a minute. It will be also with the computational activity we can have a prediction of the long-term biomechanical behavior of the device. The characterization can be of biological tissue or biomaterial or medical device from the experimental point of view, while from the computational modeling point of view we have also characterization of biological tissue and materials. We can have a modeling of medical device, and we can also say something about the optimization of surgical techniques. My talk will be on the cardiovascular field, and in particular in the stent arena. I have three examples, two related to stents and one to percutaneous valve, with different computational and experimental approach. In all of these approach and all these topics that I will show you, the importance will be given to materials, to the biological tissue, to the design of the device, to the performance from a mechanical or fluid dynamic point of view, to the loads that we need to apply or to evaluate, and how the previous part can be linked and used to study and to use patient-specific data. The approach are two. One is the in vitro one, the experimental, and the other one is the computational, and in particular it's related to finite element simulation on the structural solid part, CFD, computational fluid dynamic, and also fluid structure interaction analysis. Regarding the device, we are interested in to know how they perform before the implantation, and this could be very interesting also for certification purposes. But we want to see also how the device interact with the biological tissue. So during the operation and after the operation and also in the long-term period. Let's start with the stents. So the first example is related to the superficial femoral artery, the SFA, and this is a particular tract of the cardiovascular field, the cardiovascular circulatory network, where we have a particular biomechanical environment. So it's peculiar because we have all the different loads, so we can have torsion, we can have compression, we can have extension, axial, elongation, flexion. And when we have a disease, this can be treated with the stenting procedure, and one of the problems that can arise is the fracture of the stents due to the biomechanics that the stents are subjected to. Here is an example of fracture of stents. Okay, you can see in the yellow box and the survival curve. The material used for the stenting of superficial femoral artery are nitinol, so shape memory alloy, which be able to have high deformability in the elastic range, and this material is suitable for devices where we have repeated cycling loading due, for example, to the walk-in and the arterial blood pressure. But in particular district, the most important one is the walking, more than the arterial blood pressure. If we want to evaluate the long-term behavior of the device, we have to think about the fatigue resistance. And nitinol, which has this particular behavior as a constitutive law, you can see the yellow and the red part, are based on the strain value, more on the stress value. And the results I will show you will focus and try to evaluate the strain of the material. The design. Stents for peripheral artery have different design. Here is just reported 4 CAD model that we built based on the real device. For example, these are some pictures we took on real device, and the model tried to resemble as much as possible the geometry and the design of the real device. The characterization in the study that we show you will start from a characterization of the device itself. Then we want to know how it behaves when it's inserted in a vessel, or maybe in a vessel, atherosclerotic vessel, so with plaque, with different shape of plaque. And at the end also how this device can be studied when they are implanted in realistic or real vessel. The first part is related to the mechanical characterization of the nitinol. So when you have a stent, you don't know the material properties of the stent itself, because if you ask, they say, okay, it's nitinol, but nitinol is not steel. So each nitinol is different. You have a different surface or chemical treatment, which makes the material different. So you can have a different constitutive law. And as generally you don't have the properties from the manufacturer, you have to identify the material property of the device which you are working with. What we did, here is an example of some tests that we did. We did in terms of axial force versus displacement, and for 2 different stents, and these are the curves that you can obtain from an experimental campaign. Another important thing is that when you do experiments with nitinol, these are very sensitive to the temperature, so you have to control also the temperature. This test has been done at 37 degrees, which is body temperature. Then we try to make a replica or to do an in silico model of the experiment we did. You can see, I don't think you can see the pointer, but so on your left you can see the model which resembles the design of the real stent, and you have to select the constitutive law. So the first things that you do, you go in the literature, you take the data that you can find and looks reasonable, for example the green curve. And then if you run the simulation, so with an axial displacement, what you obtain is this curve, okay, which, so we are not so satisfied. So apart from the displacement at the end, which is imposed in some way, this is correct, but for the rest we are not satisfied. So with the manual tuning, we modified the constitutive law, the stress-strain relation, and what we obtain is a quite perfect superimposition of the two curves. Okay, we have identified the material. Is this true? So let's do another validation. So let's do another experiment. We took the stents, we do a crimping experiment, and we measure the Hope force to crimp the stent, and we run in parallel a in silico simulation with the constitutive law that we identified previously. And these are the results. So for two different stents, of course they are not completely superimposed, but the results are quite satisfactory, keeping in mind that we have run a model. So this is a way to identify the mechanical properties of the stents and the nitinol. That was just static simulation or static test. We know that the device works under cyclic condition, and if we know the stress-strain curve, if we crimp, we follow the green curve, then we have the deployment, and then in this area, this orange area, we have the cycling condition. So we work at a mean strain, and we have an amplitude, an alternate strain, where the stents work. We need the fatigue resistance, the fatigue limit. We need to know the resistance when a material, the device is subjected to fatigue. And we need to build a life constant diagram as those reported here, and this has been done with particular samples, which are wire samples, and made of the same material of the stents with the same chemical and surface treatment. And in this case, as you can see here, we have each square is an experimental point, experimental wire, and the dark one are those who were not fractured, while the white box are the fracture. We can identify a curve limit, the red one, which separate the probability of fracture with those who don't fracture. And the peculiarity of this curve is that we have two horizontal plateaux, and that we have an improvement in fatigue limit for the nitinol when we increase the strain. So we ran some fatigue testing, and in parallel we did also some fatigue in silico simulation. And to verify that the curve that we have identified, the fatigue curve, we ran a few examples, so where we applied some tensile displacement, mean displacement and alternate displacement, and one was also done in compression. And the numerical model tried to make a replica of the same experiment, and at the end of the in silico simulation we have some results in terms of mean and amplitude or alternate strain, and we can identify, for example, in this area, the location where we have the maximum strain. So this area, for example, can be designed and plotted in this area, while the strain of this area is located here. So from this graphic, we expect to have fracture here, and we expect not to have any fracture in this point. So the results from these 5 in silico simulation give us this area of most critical point, and we have a confirmation from the experiments that the fracture was identified in those areas. So also the creation of this limit curve can give us good indication to evaluate how the device will perform. What I show you is just the stent in itself. What you say, it's a free expansion, no interaction with any biological tissue with the artery. So the second step is to take this model and try to implant this in a vessel, or in something that resembles the vessel. Here are 3 different shape of vessel with different plaque in terms of 1 peak or 2 peak or sharpness. And the simulation is done before an angioplasty, which is usually done and routinely done before the implantation, and then there is the crimping of the stent and the self-expansion of the stent inside the vessel. Once this is done, then we can apply the biomechanical force that we presume to act on the stents in terms of axial displacement and bending. And here you can see the boundary condition applied. And these are some of the results. So we'll not go through all the results that we have obtained, but in general we can say that the mean strain, so it's the highest mean strain is located when we have the highest oversizing, while the amplitude strain, the alternate strain, is located where the thickness of the vessel is lower. This for the axial and also for the bending condition. If we put all this strain value in our constant life diagram, we can also see the influence of the different shape of the plaques, or the double plaque, or the low sharpness plaque, and we can identify which are the areas of most stressed point. So in general, the message from this simulation is that the shape of the plaque and the vessel change the behavior of the device. So it's not enough just to evaluate the device in its free configuration, but we need to investigate how it behaves when it's implanted in a vessel. What's next? So what I show you are just idealized model. We can go now through very more realistic and try to use patient-specific data, so and in vivo data. So we know that now with imaging, it's easy and possible to reconstruct in a three-dimensional space the geometry of the vessel, in this case the superficial femoral artery. It's possible to run CFD simulation. It's possible to run finite element analysis, as those I show you. And what will be interesting will be to follow. So to go, if you have follow-up data, to see how the stress and strain, how the fluid dynamics could be related to the failure of the procedure. And again, another thing I think it's important for future study is to work on a multi-scale level in terms of time, but also in space. So we have our reconstruction, our vessel, and we can evaluate, for example, wall stress, wall tension, endothelial shear stress. So we are at the level of the tissue and time of seconds or a few minutes. And if we use this data to be used to get a gene network, so also for a gene therapy, so we can link this value with remodeling, with cell apoptosis, with the position of extracellular matrix, which in turn will modify the lumen, and so we can link the fluid dynamics and mechanical quantities to the success of the procedure. Now I show you another example. It's related to percutaneous valve. I don't know if all of you are familiar, but it's always based on stent technology. Here you can see a valve which is inserted through the femoral artery. So with the catheter, it's moved along the aorta. So you go to the ascending aorta, and then you position the valve in the annulus, so in the pathological valve. Then you can release, in this case it's a self-expandable valve, it's released, and so it squeezes the leaflet, the original leaflet, and it works not perfectly, but it should work like a natural valve. So this is very technological and quite new, so it's around 15 years that this technology is being used. The valves are different, so we have different kind of valve, and so the design is different for each valve. And what is possible to do, or what ideally we want to do, so we want to evaluate the long-term performance of the valve and the performance in general of the valve, and to see how the valve performs when it's inserted in a patient-specific anatomy. This is more complex, it's a complex problem because of the boundary condition, because of the limited in vivo measurements, and also because here it's important to take into account both the structural and the fluid dynamic part. All these have influence on each other. So which is the methodology, which is in my opinion is the best one to tackle this problem, is the fluid structure interaction model. Here is an example, very simple example of a steel bar which falls into the water. And the steel bar is described by Lagrangian elements, if you use the finite element codes. And the air or the water is used is based on Euler element. So if you have this steel bar, what we have could be something like this. So you have the fall of the bar inside. I don't know if this simulation is right, it's correct, but it's nice. And so I think this could be a way try to use this methodology apply to a valve. And this is what in our laboratory we have done. We started, as in the previous one, with a validation. Let's see first the validation process, and then we'll try to apply to patient-specific case. This is a valve, a percutaneous valve is a prototype, it's not commercialized, and has been done in collaboration with the Helmholtz Institute in Aachen. We have the real device, and we have on your right the in silico model. This valve has been inserted in silicon holder, and this has been reproduced also in the computational simulation. We have done accelerated fatigue testing, and here you can see the model. The blue one represents the fluid. And the boundary condition in this case is the pressure gradient that has been measured during the in vitro test. We want to make a replica from a computational point of view of the experimental test. And we did this comparison in terms of opening area of the leaflet. Here you can see the in silico on the top and the in vitro on the bottom. And we measured the area at the maximum opening. We have a really good agreement, while during the cycle there was some discrepancy. And we have additional information regarding, for example, the fluid dynamic field, like pressure, velocity, or streamline. And in addition, we can also have, as in the previous case, a description of the mechanical behavior of the stent frame. So the strain which are in each point of our valve. We can plot this in a constant life diagram, and if these are the results, we can say, okay, we don't have any or we don't expect any fracture. And when we apply 100 millimeter of mercury as a gradient. If we do a simulation with 150, so the strain field is different, and we expect to have some fracture, or at least it's more dangerous, the mechanical solicitation to the valve. And this was observed also in another accelerated test where we apply 150 millimeter of mercury and we observe a fracture. Of course, no, it's not true, but we didn't do a big campaign. We have just done some tests, so a couple of tests which confirm that increasing the gradient, you can have a fracture, and this is also predicted by the in silico simulation. If we move now to patient-specific data, with MRI it's possible to extract the aortic root, it's possible to make the mesh, and it's possible to simulate the positioning of the valve inside with the crimping, with the release, and the interaction of the valve with the aortic root. As a boundary condition, we use reasonable or expected ventricular and aortic pressure, and as in the previous case, you can have a description of the kinematic of the opening and the closing of the valve, and velocity, field, pressure, and streamline. And again, it's possible to have a description of the solicitation of the strain on the stent frame, and if we put this, the gradient that we apply on the in silico simulation, it's 100 millimeter of mercury, and we can observe that using patient-specific data, the stress change. So it's important to know that if we do an experiment in ideal condition for certification purposes, not necessarily what we can expect when we apply the device in vivo is the same result. Here is the video which summarizes all the simulation with the crimping, with the interaction with the aortic root. The aortic root is elastic, so it moves, and you can see on the right side, here is on the right side you have the stress, and you can observe also that the valve moves inside, and you can evaluate also the reaction force on the aortic wall. What we can do in a better way. So we can apply what we have seen in in vitro study also to patient-specific cases where you can take into account also particularity like the calcium, which is on the leaflet, as is shown here. So here we can detect from CT scans the calcium and exactly the positioning in the 3D space, and we can build an FSI model of our aortic root, applying the pressure which was recorded during the operation, and these are some of the results of the preoperative situation of the patient. You can compare your results with the results that with the clinical data that you have. So just to set up a correct model. When you have a model like this, and you can think to make a model of the valve, you can try to crimp the valve, you can position the valve inside the patient-specific model and make a more realistic simulation which take into account, for example, in this case also the presence of the calcium, and then you can evaluate clinical parameters like the regurgitation, if any. The last example is related to coronary stents, and here you can see in this slide an experimental part of the OCT, which is the Optical Coherence Tomography, which is near-infrared light, which has had high resolution up to 10-20 microns, and this technique allows an exhaustive picture of the blood vessel lumen before and after the stent deployment, and it's really powerful for small vessel. And if you combine the angio, which gives you the three-dimensionality, because the OCT is just a stuck frame, and you don't have any 3D information on the spaces, so basically you need at least the center line of the vessel where you can align these images. But if you combine the OCT with angio, so CT, plus an in vitro model, maybe you can give an answer about the hemodynamic assessment of endothelial shear stress, and to see if these forces, which is exerted on the vessel lumen, have an influence on the success or failure of the stenting. We did again a procedure where we start from a validation process. So we built a CAD model, we 3D print this CAD model, we implanted inside a stent, and we did some angios images. I will come back later on all these steps. We acquired the OCT images. We did also a micro CT scan of our stented model, and we made both reconstruction from the micro CT scan and also from the OCT images, and we want to compare those with the aim to have a methodology, an algorithm which allow us from in vivo OCT acquisition to reconstruct a stented vessel. So this is the creation of the CAD model, so it's something that we really know. So we know because we try to have a vessel with curvature, but the CAD file was designed by us, so I know exactly where is the center line, everything, the vessel lumen. And this was 3D printed. Then we went to a catheterization theater, and we did acquisition angiographic images of our 3D sample with and without the stent. So we implanted the stents, and we did an OCT acquisition. The advantage is that we avoid any vessel movement, which of course could be present in vivo acquisition, and we know everything about the geometry. The algorithm that we developed allow us to identify the lumen contour and the stent struts. Then we align all the lumen contour and the stent struts along the center line, and you can find more data on these two recent publications. In parallel, we ran a micro CT scan of our sample, and which mimic software, we reconstructed our sample, and then we make a comparison of the two, which there was some discrepancy in terms of the alignment, so on the twist angle, but the results were quite satisfactory. Keep in mind that the distance, the area with the distance more than 0.25 millimeter are those reported in red. The second point is to have also the stent inside this vessel. So we have the stent's point cloud. We have a straight configuration of the stent. This is no, because so we know the stent that was implanted. And so with a manual, we define some handle point, and we move the center line on the stent points. And when we have an alignment of the stent point, then we could in some way sweep the cross-section of our stents, and we have a three-dimensional model of the stent. And when this is done, so we can compare the micro-CT reconstruction with the OCT-based model. We can identify malapposition areas. So malapposition is when the stent is not opposed to the wall, so you have a gap. And if you think that you want to study the fluid dynamics, this gap is important to be taken into account. And we made a quantification, and we were quite satisfied by the results that we obtained. So now we have a sort of validation of our process, and we want again try to apply this to in vivo cases. So from the angiographic view, it's possible to reconstruct the vessel, or at least the center line. The OCT images, we can do the process with these images as shown before, and this is a result on in vivo case. So we have a precise, a very accurate description of the vessel and the stent. And we can then run CFD simulation. In this case, this is what we want to study, and you can observe here, for example, these are some struts which are malapposed. So you have the flow which goes around the struts. Evaluating the shear stress is a way then to try to, when we will have just here, for example, two samples, but in the future we plan to have a lot of these cases, and when we have a big cohort of patients, we can make some correlation with the wall shear stress or the force exerted on the endothelial cells, and to see if there is any correlation with the in-stent restenosis. We have also some, in this case, for some patient, we have also an OCT at follow-up, which is not routinely done, but in some cases this is done. So I come to a conclusion. So the first one is that the geometry is really important, the material properties are really important, and I don't go through all the three different aspects, but in all of these three different examples I show you, the patient specificity is something that is really important to be taken into account. And lastly, it's important to think about also a multi-scale model. So how to use these kind of results, which can be at a high level in terms of geometry, or in time, so a very short time effect, how to have a forecast for a long-term period. What I show you, basically, I show you some mathematical model. All of you know that, so mathematical model is try to simulate real-life situation, and we would like to try to forecast the future behavior. And why? Because we want to have to test some hypotheses with some numbers. Most of us are engineers, so we like numbers. And once we have a model, we want to change some parameter. This is one of the advantages of the model. So we just change a number, a parameter, and we want to see which are the effects. So we run a simulation. So we start from the physical reality. We make observation, we collect data, we go in the catheterization room, so we have all our data, and we build our mathematical model. So we can write a equation, or we can have a three-dimensional model, but this is the same thing. We run our simulation, we have our results, and we make an interpretation of our results. So, and if we are not happy, we go back. We try to refine. And so we make a loop. So this, what does it mean? It means that all models are wrong. This is not my sentence. This is a sentence of Sir Box, who concluded also that it's true. They are wrong, but some of these are useful. So an example of why they are useful we can find in the last call of the Horizon 2020 call, in the personalized medicine call, where I choose these two sentences that say that in silico approaches is expected to lead to a reduction of unforeseen serious events and to optimize that integrity during clinical testing. Or again, in silico test results will provide quantitative risk of potential complication related to specific feature of new devices. So this is the way that how models can be useful. And lastly, this is the last question, it's important in my view to combine experimental and computational results. We have also to keep in mind that in general, so a simulation is something that nobody believes, of course, except the person who made it. But an experiment, it's true that it's something that everybody believes, and I also here except the person who made it. It's not my sentence, it's an adaptation of a most famous person. So these are the persons I would like to thank from my laboratory. And I'm really grateful also to the enthusiasm of young people. And again, muchas gracias.
Thank you very much for a very exciting keynote lecture. Are there questions from the audience to the talk? We have a microphone, so if you hold your hand up, we can bring you the microphone. There's one at the front.
Well, thank you very much for this impressive talk. That's just a curiosity. So you've showed the fluid structure interaction, and you've shown a very nice arterial wall with structural hexahedral mesh. And then I'm wondering about your capacity to personalize the thickness of the wall and preserve this mesh structure. And if you cannot, have you an estimate of the impact on the uncertainty of the simulations?
Okay. This is a good question, because I didn't tell you that for what we have done, we assume to have a thickness proportional to the diameter based on literature data, depending on the data you have. Sometimes if you have maybe CT, it's possible to have a more precise description of the tissues. If you have MRI, it's more difficult, of course, to have this information. So we were not able to detect, in this case, the real thickness of the vessel, and we didn't do any study regarding the influence of the sensitivity analysis of the thickness wall on the results. Of course, this is one thing that we are planning to do, especially also to try to change the material properties of the wall. So we are planning to see also the influence to have fibers inside, but the precise simulation are also computing demanding. So more you add information in terms of complexity, this makes longer the simulation. So one simulation like this was for one cardiac cycle is more than 2 days of running on 32 CPU. And I'm quite confident in the future this will not be a problem, and that we will increase also to have a better description of the problem. We also, what we want to do, for example, in the percutaneous valve, we want to estimate the regurgitation. So we have clinical data to evaluate how much flow is regurgitant, if any. In this case, I don't know how much complex we need to make a model to answer a specific question. If it's just that, I would start from elastic material and see not just on one patient, because one patient doesn't tell you the truth, but and then you move toward to understand something more complex. But it's an issue. This is for sure an issue.
One thing I was curious about is you concentrate a lot in the presentation on the failure of the stent material itself. How critical are the leaflets? I mean, these are highly nonlinear materials, I assume, incredibly thin. They probably flutter or do strange things. How rigorous is the material characterization of this part of the valve, and do you see limitations in the simulation of that component?
Okay. So before giving an answer, which I'm not sure to have an answer, but I tell you my experience with the first valve I studied from a computational point of view was the percutaneous valve. Was back in, I think, in 2006 and 2007 when I was collaborating with in London, the Great Ormond Street, and at that time there was the first experience with the percutaneous valve. It was a platinum iridium frame with pericardium. I don't remember if it's porcine or bovine. I don't remember which kind of valve. And one of the main issues from the cardiologists were the leaflets. Okay, we need to concentrate on the leaflets. I remember that the cardiologists went also to talk with people making polymeric leaflets to have more resistance, but the first failure on the patient were not the leaflet. So the leaflet was not an issue. The failure was on the stent frame. And so I don't know if the leaflet is a problem. No, I think there is a good, long experience with prosthetic valve. So the material is the same, so when you biological valve. And from a modeling point of view, I think it's important to take into account. So to have fibers which describe, because this can have influence on the kinematics. So I think it's important to be done and can be done. So we are working also on that. And one of the difficulties sometimes, for example, for my group who is working on with commercial software, which has the advantage to be validated, is then the ability to go inside and try to implement this kind of constitutive law. But again, this is another part which is important in the description of the biological tissue.
Other questions?
In more elaborated fatigue life prediction theories today, they are work mainly or express fatigue life in terms of probability to failure. Do you think it's really difficult to incorporate that in your model? Or is it possible? It takes too long? You need a lot of data?
Well, there are different theory on the fatigue, so different criteria. And I think this, if you have a good description, and you can use this kind of data to make a better prediction of the fatigue. But of course, I would use also an experimental campaign, so to see how then this model are good model.
Other questions from the audience? Here's one in the front middle. No, you went too far. He's here.
There's another one there.
Yeah. Oh, sorry.
So my question will be quick. My question is more perspective. This is a world driven basically by the market, so sometimes we are investigating devices that are already out of the market. This is moving very quickly. What can be the secret to switch the trend and the key factors to study just to avoid this issue, which can be a problem, that you end up to study something that it's already out of the clinical turnover, which is extremely fast. Thank you.
It's a secret, so I don't give you an answer.
That's why I asked it in front of all.
I don't have an answer for this. When we do a model, so we sometimes we don't work in strict contact with companies, so we don't know what will be the future, and we try to understand at least what we have sometimes in answer, and try to apply this or future application. So I really don't have an answer to this point, but from the past I think you can learn a lot. So my point is that if you're able to do, for example, a good simulation on a device that maybe is also old, I think it will work also on new product, on new devices, and I don't see this big problem, but I don't think there is a secret.
Okay. And there's a question on the right. Sorry for making you walk so much.
Thanks. I was curious about the difference in the nitinol behavior from the literature data you had shown and then the results you had after your structural characterization. Why do you think there can be such a large difference? Can it be metallurgical influences?
You mean from the nitinol itself and so stents and stents, so because the nitinol is different from one device and the other one. I think I'm not really expert on this, then I can rely with a colleague of mine who's here and she can tell you much more than I can tell you, and there is also a presentation tomorrow, but I understood that all the treatment that you do on the nitinol has a big impact on the final mechanical properties. Depends also by the thermal treatment you do, so if you change the temperature you can have a different disposition inside of the material, and the final behavior will be different. And also the beginning, the way they produce, so the company produced the tube from the ingot, could be another point that even if the composition is the same, the final behavior, so the behavior of the nitinol material is again different. So you have to know which is the composition, but you have to try to test the material, and in this particular case, so it's important to test the material with the size, so the struts. So if it's 10 microns, it's important that you make a characterization of 10 microns, because if you do with the same material characterization of 1 centimeter specimen, the results could be completely different because they have a different behavior. This is what I learned from the nitinol, which is sometimes it's a nightmare, but it's also something which is intriguing, and it's nice to go because you always discover something new.
Okay, I thank everybody for the really interesting questions, also for a very enlightening keynote speech. I'm going to close the session now so that you have time to get to the next parallel sessions. Thank you again, and enjoy the rest.
Che bello, io